Okay, we have been talking about how matrices represent linear functions. Now we're going to do algebraic operations on matrices and relate that to the linear functions that these matrices represent. Now, most likely you're familiar with addition of matrices or multiplication of matrices by a scalar. We'll do that again, but we'll also give some theoretical underpinning that should give you deeper insight. So let's talk about sums and products of matrices with constants. That's why we say scalar product, not matrix product. We're just going to be multiplying matrices by constants and not by other matrices. Okay? So remember that we're identifying matrices with linear functions, and let's look at some operations on linear functions. In particular, we can talk about the sum of two linear functions. So here f and g are linear, and we can define f plus g operating on vector v as the function that takes v to f of g plus g of v. Similarly, we can talk about the scalar multiple of a linear function as the function that takes the vector v to r times f of v. It's not difficult to show that these two mappings are linear. If f and g are linear, then f plus g is linear. If f is linear, then rf is linear. So let's see how this same operation, these same operations are represented in the matrix picture. Right? We know that f has a representation in terms of two bases, and g also has a representation. So let's see how we can get a representation in terms of two bases, b and d, of the sum of two functions and the product of a function by a scalar. All right, let's do an example. So let's take this particular linear map that's represented with respect to the bases b and d by this matrix. Now, since we're just going to be operating with the matrix, we don't particularly need to know what b and d are. And that will not change our answer. Okay. Now, suppose f of v is w, and suppose we have representations of v with respect to the domain basis of v1, v2, and representation of w with respect to the codomain basis of w1, w2. Now, consider the function 6 times v. 6 times f. Well, 6 times f operating on v will give me 6 times w. Okay? 6 times w can be written in terms of the d basis in this way, where w1, w2 is the representation. So you can see that the representation of 6w is simply 6w1, 6w2. All right. This seems obvious, but you do need to go through these steps, that the representation w1, w2 means that w is w1 delta 1 plus w2 delta 2. And if you take 6w, then you multiply the two components of the vector w by 6. Okay? So, in other words, you take an input vector. If you're looking at the function 6f, then the output entries are 6 times as big. All right. Now, if we consider the action of f on v, if we do it in terms of the representations, if we're looking in the representation picture, then this result will be the representation with respect to d of f of v. But that's how we get it. We take the matrix and multiply that by the representation with respect to the domain basis of the vector v. Okay? If we do this matrix multiplication, we get this result. On the other hand, if we want the representation with respect to D of 6f of v, well, we have to take the representation of the linear function 6f, multiply that by the representation of v, and naturally we get this result. Now we can rewrite this as v1 times v2, that's the same thing as v1 times v2, v1 v2, times this matrix 12, 6, 18, 24. I'll just write that there. What that means is that we can replace this original matrix 2, 1, 3, 4 with 12, 6, 18, 24, and that gives us the representation of the function 6f. All right, so we're relating scalar multiple of matrices to scalar multiple of linear functions. Okay, so this result should be no surprise, but we do need to go through the verification steps. Let's do the same thing for addition. So let's consider two functions, f and g, that are represented by matrices capital F and capital G, and consider the matrix that represents the function f plus g. Okay. Now, I think it shouldn't be a surprise what that matrix will be, but let's go ahead and verify. All right. If f of v equals u, where v is some arbitrary vector in the domain, and u is a vector in the codomain, and if g of v is equal to w, then this is what f plus g does. Okay, v takes f by f plus g takes f plus g takes v to u plus, this should be a w here. Now I can write u in the d basis as u1 delta 1 plus u2 delta 2. I can write w in the d basis as w1 delta 1 plus w2 delta 2. Arrange the components, and in terms of the d basis, f plus g of v is equal to this vector here. Okay. So if you write that in terms of representation, the representation of f of v is u1, u2. The representation of g of v with respect to the d basis is w1, w2. And the representation with respect to d of f plus g of v, that's from here. We look at the components, it's u1 plus w1, u2 plus w2. Okay, so let's relate that to matrix multiplication. So here we have representation with respect to d of f of v. This is, remember, this is the representation with respect to b and d. It's not working there. I don't know why it's not working. Of f, and this is the representation with respect to b of v. That's how we get this representation. All right, through this matrix multiplication, we arrive at this result. Through this matrix multiplication for g, we arrive at this result. And we saw on the previous page that if we take u plus v, we'll be just adding this vector to this vector. So we're going to get 7v1 plus 9v2 goes in the top. And from here, 10v1 plus 10v2. That's the representation of f plus g operating on v1, v2. Okay. This actually shouldn't be here. You should just have representation of f plus g. Okay. So we want to get a matrix that gives us this result when acting on V1, V2. And clearly, if you take this matrix and multiply by the column vector V1, V2, I get this result. The upshot is that the representation of F plus G turns out to be exactly the sum of this matrix, which he called capital F, and this matrix, which he called capital G. Okay, so we can define the sum of two matrices and the scalar multiple of a matrix. Scalar multiple of a matrix is the result of entry by entry scalar multiplication, and the sum of two same-sized matrices is their entry by entry sum. So that's what we saw on the previous slides. Okay, so here we have A, B, and C. You can add A and C entry by entry. 1 plus 1 gives me 2. 2 plus 8 gives me 10, etc., etc. I can multiply B by 5. I multiply each entry by 5. 5 times 0 is 0. 5 times 0 is 0. 5 times 2 is 10. 5 times 9 is 45, and so on. If the sizes aren't matched, you can't define the addition. You need to add same-sized matrices. Same number of rows, same number of columns. Okay? Let's generalize the result that we showed for the particular case. Let H and G be linear maps from V to W, represented with respect to fixed bases B and D by the matrices capital H and capital G. And let R be any scalar. Then, with respect to these bases B and D, the map R times H is represented by R capital H. Remember, capital H is the matrix that represents little h. And the map H plus G from V to W is represented by the sum of the matrices corresponding to little h and little g. Okay? The proof is just to generalize early examples. It's playing around with indices. It's easy to do specific numbers. You do the same sort of manipulations with arbitrary matrices. Definition: a zero matrix has all entries 0. The zero matrix is the identity element for matrix addition. I think this example makes it clear. A zero function Z is the identity element for function addition, and the matrix fact accords with the map fact. Okay, let's stop here.